Let's look at two questions. One is a linear magnetic circuit question. One is a nonlinear magnetic circuit question. First, we have to identify what's going on here. What is a linear question? What is a nonlinear question? Well, what matters is what it is made out of. So if you are analyzing some magnetic circuits, it depends on the material. So what we should be really looking for when we first go to attempt a question like this is that I want to see what it's made out of. Brass is very different than cast steel. Brass is somewhat of well, it's definitely got a constant relationship between flux density. And remember, that's our amount of magnetic flux over the cross-sectional area and magnetic field strength. It's a constant relationship. It is that of free space. So we have to know, we have to remember that the relationship between the flux that's in the circuit, which is measured by flux density normalized, right? We have to remember that it's that the permeability or the amount that this material wants flux to get established is called the permeability, and it's always the same. So permeability we write like this, and it's constant. It's always the same. And whereas for a cast steel, as we get more and more magnetized, the field strength gets stronger and stronger, or as the field strength gets stronger and stronger, as induced by the MMF or the ferromagnetic force, which you can change yourself, right? Because it is a function of, yes, magnetic field strength times length, but also of your current times your number of windings inside a coil. So as you increase that for H, you're going to get more and more magnetized, which means you have more and more flux going through your circuit. So here we go in, say, something like cast steel, a ferromagnetic material, we get more and more magnetized as we turn up the current in our coils. And then until you get a point of saturation, you don't get everything for free forever. You saturate. This is saturated. And this is a nonlinear relationship. This is a nonlinear relationship. However, this brass core always stayed the same. And permeability is constant. Permeability is actually that of free space. So it rides the relationship between B and H stays exactly the same. If I were to plot permeability and flux density B, it would be straight at mu equals 4 pi times 10 to the 7, -7 henries per meter. Stays the same. Now, it's actually the slope of the BH curve, but the BH curve sits like way down here. And this, for all intents purposes, is straight. And what is permeability? We have to remember that permeability, well, of course, it's a tendency to want to permit magnetic flux to develop, but permeability is rise over run of this curve. Permeability equals rise over run of this curve. And if this one is rising and running at the same rate, because that's a straight line, right? So it's constant. And this one, well, rise over run is a slope, right? This slope is always the same. This slope here we go. It's a pretty steep slope. And then it's not as steep. And then it's not as steep. And then when it's saturated, it's not as steep. We would never take this one, but we would take around about here or whatever. But the permeability is nonlinear. It varies. So this material that is cast steel, really, really happy to get more flux established at the beginning. Then it gets a little bit less happy to establish flux. And then it says, no, no, no. I don't want any more of this flux. No more flux. Okay. So that's the difference between a linear question and a nonlinear question. And other than that, if we look at how these questions are given, so we really had to know whether we're dealing with a linear material or a nonlinear material. That's our first step. Our second step is to just look at what this what the geometry of the problem is. And this one is a circular cross section. It's a toroid. Toroid means kind of donut shape. So these are both kind of donut shapes. This one has a circular cross section. This one has a square cross section. This is nothing. This is nothing to do with whether it's linear or nonlinear. We don't care about the shape. Okay, so what makes this a linear question is the fact that it is made out of brass. What makes this a nonlinear question is that it's made out of cast steel. Done. Now you know what kind of question you're working with. But it has nothing to do with the geometry. But there it is. It's circular cross section, or sorry, it's a toroid. And if I took a cross section of that toroid, it would be circular. Here's a cross section. I go like this. I show that it's a pie. I'm cutting a cross section. This one is also a toroidal shape. And I'm going to cut a plane of this, but it has a square cross section. This one has a square cross section, it says. All right, no problem. Then it has 1,200 turns in each one, which has nothing to do with whether it's linear or nonlinear. Here we go. Here are the turns in each one. This one has a current of 1 amp. This one has a current of, we don't know. There are n equals 2,000 turns in this one. There are n equals 2,000 turns in this one. Again, nothing to do with whether it's linear or nonlinear. And let's see, in this one, I want to find out what is the total flux created. And in this one, I want to know the total current given that it has this much flux. So we have to approach these questions differently though, because for the first question, it's linear, therefore I just substitute in permeability as a constant, and the constant is going to be that of free space, which is 4 pi times 10 to the negative 7 henries per meter. Whereas this one is nonlinear, I'm going to have to find a BH curve for cast steel. I'm going to have to solve for either B or H, whichever one is easier to solve for. I'm going to assume B because I have this outer dimension and inner dimension. So then I know what area is, right? And so I'm going to solve for B because I know flux over area. I'll come over here and I will grab an H value. I'll probably go rise over run to get permeability and then solve that question. So that's how we have to approach these two problems. So let me do this problem. Let me do these two problems just sort of with the math. And I won't substitute in, or else it'll be a really, really long video to substitute in all of the math. But let me just put the equations that I would use for this nonlinear problem, and then I'll put the equations that I would use for the linear problem. So let's go ahead and solve it. And remember, I'm told the inner diameter of this, so I do know the cross-sectional area. All right, so for this first one, I think what I would first do is I'd say, what are you asking for? So I'll just put the solution steps here for you. So the solution steps, I would first say I'm the type of person who always solves for, what is asked for first, and then I substitute in from there. which is backwards to what most textbooks do, but that's what I do. So I would say, okay, well, we're looking for uh, how much total flux will be produced. Well, I know that the total flux is a relationship between that force and that reluctance. This is sort of like my V equals IR equation in electrical circuits, right? And so that's what I would use first. And then, well, actually, I might as well just solve it. So that's my 2000 turns. And then I don't have R yet. So as a, oh, hang on a second. I actually don't have FM yet. So then as my second step, I would then calculate FM because I need that for the numerator here. FM is N times I. I know I have both of those. I have N here and I have I here. So that would be my 2000 turns times 1.0 amps. And that's where I got that 2000 amp turns. So now I know this numerator. As a third step, I'm going to have to calculate the denominator, which is RM. Well, we have sort of a bit of a famous equation for that. It's mean path length over the permeability times cross-sectional area. Well, that permeability is that of free space because it's brass. So I'm going to put a note over here. Mu naught equals 4 pi times 10 to the negative 7 because it's brass. So brass has a permeability close to free space, and that's what we always use. For here, I best calculate the mean path length. So the mean path length, let's do the mean path length in blue. Mean path length means the middle spot that this flux would be traveling. Well, if I take a look at the inner diameter is 8 centimeters and the outer diameter is 12 centimeters, then to the middle must have been 10 centimeters. So what I'm looking at for mean path length is sort of a path that has radius equals 10 centimeters. That's one way to do it. And then you can calculate the circumference, right? Circumference equals pi. Sorry, these are diameters. These are 12 centimeter diameters, 8 centimeter diameters, and then this would be a 10 centimeter diameter. Diameter of the mean path length is 10 centimeters. So pi d, which would be pi times 10 centimeters, would be that mean path length in the middle. There's so many ways to do that. I could say pi d of exterior minus pi d of, or plus pi d of interior divided by 2 to get the average path length. So many ways to do it, but I'm just going to use pi d there. Pi times that middle diameter, pi times 10 centimeters. I have to remember that I'm in centimeters now. So now I'm going to go into permeability. So permeability is that of free space I got from up here. So that is 4 pi times 10 to the negative 7 henries per meter. Oh, we have to recognize that I'm in meters there. And then I need to do a pi r squared of the cross-sectional area. So let's do cross-sectional area in another color. Here's my cross-sectional area. And from my problem, if I were to look at this head on, this was 12. And in here is 8. Then there must have been 2 here. which means the diameter here is 2, excuse me, centimeters. Diameter there is 2 centimeters. Therefore, radius of cross-section is only 1.0 centimeters. I say 0.0 because it's a measurement. We should have significant digits. So therefore, area is equal to, well, our equation is called pi r squared, right? It's pi r squared equals pi 1.0 centimeters all squared. So I can put that in there, pi 1.0. I'll do the units just like I did up here, squared, centimeters squared. And now I do have a centimeter on the bottom and on the top. And I'm not going to go through all of the conversions and everything to work that out. I will leave that up to you. And I will just answer in orange here. That's going to all work out to 7.96 times 10 to the 8. If you work out your units properly into amp turns per Weber. And I kept the turns. So now I know R and I know FM and I can solve. So sub into 1, what I wanted to solve for. So now FM was 2000 amp turns over 7.96 times 10 to the 8. I'm keeping the proper number of significant digits here. And that would be 2.5 times 10 to the negative 6. Amp turns cross out. Weber is in the denominator of the denominator, so it comes to the numerator. And that makes us feel happy because we want it to be in Weber. And that's how much flux is going through this core. We asked how much flux was produced through this kind of donut-shaped core that is made out of brass, that is linear. It has the permeability of free space. It has 2,000 turns with 1 amp running through it. Then how much flux actually gets developed in there? This is the answer, 2.5 times 10 to the negative 6 Webers of flux. Now, that's the linear question. Linear questions are significantly easier. This video will be way too long if I give all the math of the nonlinear question, but let's just put in the formulas, or let's just kind of look at the relationships we would be using for this nonlinear one. So in the nonlinear one, let me just kind of try to erase this thing here. Can't get rid of this. We are not looking for the flux in the nonlinear one. In this one, I mean, we could be looking for the flux, but this question happens to be asking for something else. This question happens to be asking for the current given the flux. But other than that, it's the same type of question. So let's just gain ourselves some room here and solve this one. All right, so you're going to have to maybe take a screen capture of the question. Or maybe I'll just try to take it down here. There we go. Now I think I'm set up so that you can see the question and the solution here. So this one, again, we looked at whether this was linear or nonlinear. We decided that this is a nonlinear question where because it's made out of cast steel. So we're going to have a BH curve that looks like this over here. We're not particularly happy that we have a nonlinear question, but that's what we have. So let's show you how we would solve this. It says how much current would be flowing. So I like to answer my math. I'll just say steps, and I won't substitute them all in. It'll take forever if I do. I equals, so I would use this, hang on. I'll put this in the format we usually use it. We should have memorized that the amount of magnetic force is related to the current times the current in amps times the number of turns through this circuit. So then I would rearrange this equation and say, oh, in this question, I want to solve for current. So this is the equation that I'm going to use. And I already know N, so I can substitute right in there. But I need to know FM. So what's FM? Well, FM also has another relationship. Of course, it's sort of like an Ohm's law relationship. It's sort of like voltage and current and resistance in an electric circuit, but it's force and flux and reluctance in a magnetic circuit. So I'm going to use this equation and I'm going to solve for it. I'm going to substitute in, and if you do, you'll find that this is 744 amp turns. So there we go. Am I finished? Oh, you actually can't do that yet. You do have flux, but you don't have RM. So in order to get that RM, let me see. It's hard to do without substituting in. I don't have the RM, so I have to remember, I have a few relationships about reluctance. It has to do with the mean path length that everything travels and the permeability times the cross-sectional area. And that's when things get hard. In a nonlinear question, this is where it gets hard. And I'm just going to actually draw that here. This is where non-linear questions get hard. And let's face it, most magnetic circuits do have an iron core and are difficult. So what we have to do now is step 4, which is difficult, is we have to figure out the permeability. And it is flux density over magnetic field strength. And it has to be from the BH curve. Well, I don't know permeability. I don't know magnetic field strength. So I must find permeability. I must find, sorry, I called that permeability. I don't know flux density and I don't know magnetic field strength. So I must find flux density. Well, flux density is the amount of flux going through per cross-sectional area. I have, yes, been given the amount of flux, and I have, yes, been given the cross-sectional area because it's up here. I have the dimensions. This was outer diameter is 15, inner diameter is 12, 13, 14, 15, right? So then it must be 1.5 by 1.5. It says it's square. So that's in centimeters. So I do have cross-sectional area. All right, good. So I can substitute in my values here. I'll just do one of them for you. We were given this in Webers. And that's just my flux. And we know the area because we know the geometry of, like, you know, a square. But you might kind of forget the area of a square. That would be my 1.5 centimeters. And I didn't mean that in a rude way that you might forget how to deal with the area of a square. But remember, we have to take that 1.5 centimeters and we need to square it, right? That's it. But we need to be working in meters. So don't forget that when you are converting to meters, we know there's 100 centimeters in a meter, but we have to remember that it is squared. So that's a common problem. So make sure that you get all of that in there properly. And when you do, you'll get 1.33 Tesla here. Then it's still difficult, right? Because you're still looking for this permeability. This is permeability, which if you don't know, you should know, it is the slope of this BH curve. So you go and you find this curve and you find it for cast or whatever we're dealing with. What are we dealing with here? Cast steel. And so now I find this 1.33, 1.33. I go over on this curve, I hit the curve, and then I go down to find H. And so permeability is the slope here. It's the slope, which is rise over run. What is H when I hit it? It's actually 1750 on the chart that I looked at from the curve. So it is rise over run, and it is going to be then 1.33 over H. And I think like at this point, I can kind of go backwards and substitute in. Actually, I still need length. And that's just the mean path length. So mean path length, kind of like doing that in blue for some reason. Mean path length is kind of where these flux lines are flowing. Here we go. And I would say that they are, they're a circumference, because even though this has a square cross section, you have to make sure that for mean path length, you're looking down on this. It still looks like a donut. Okay. We don't cut a cross section for mean path length. It's circumference calculation, pi d. Well, what is the circumference? Well, it's pi, pi d. What is the diameter if I'm looking at pi d? Well, it's this middle diameter. It was 15 to the outside. It was 12 to the inside. So it must be 15 minus 12 over 2 centimeters plus another 12 centimeters. Give this video a pause and think about what I'm talking about there. There's lots of ways to do it. And you might say, that's a really dumb way to find diameter. And maybe it is for you, but there's lots of different ways to do that. And I end up with 0.424 if I converted that to meters. Okay, now I can substitute everything in because, well, I have trouble doing a video without substituting it all in. Let me just substitute it all in black here. So now I know L and I know A, 0.424 meters over the permeability. I figured out where. Oh, I haven't figured it out yet, but it's rise over run over here is permeability. (1.33 Tesla over 1750 amp turns per meter, which gives me 7.60. Oops. Times 10 to the negative 4. You have to make sure that your permeability numbers are all really, really small. Negative exponents. Times 2.25 is the cross-sectional area, times 10 to the negative 4. Meters squared. And this one was in henries per meter. So that is equal to 2.48 times 10 to the 6. Amp turns per Weber makes us feel happy because now That's good. Now I can sub into FM here. Now I'm doing math backwards, which is the way I do not like doing math, but let's do it anyway. 3.0 times 10 to the negative 4 Weber was given in the question times RM down here. I'll just say times RM is going to equal 744 amp turns. Hate doing math backwards, but here we go. I'm doing math backwards. I have my 744 amp turns. I would prefer to write out all of these equations again. That's how I would do this math. Over N, which is given in the question, it's just 2,000 turns. Turns cross out and I get amps. Do I want amps? 0.37 amps. Do I want amps? Well, it says how much current must be flowing. Current is in amps. Therefore, 0.37 amps are flowing to make that much magnetic flux inside this thing that looks like a donut, but it actually has a square cross section that is wound to 1,200 turns. 1,200 turns? It's 2,000 turns. This is 2,000. 2,000 turns. And that's my answer. So the difference between these two questions, is the material. And cast steel says, oh, I have to go and get this BH curve, which makes things difficult. Whereas if it's made out of brass or air, etc., then it's not difficult. It's just the permeability is that of free space.